So I'm summarizing that right here. When the data has more spread, the absolute deviations get larger, and the MAD gets larger, because the MAD is just the average of the absolute deviations. It's the mean of the absolute deviations. Now, why can't you just find the mean of the regular deviations? I mean, why can't you find the mean of this column right here? The reason why is because these values always add up to 0, because the positive and negative numbers cancel each other out. That'll always happen in any data set. So in order to keep that from happening, you have to find the absolute value of each deviation. And that when you find the absolute values, all of the deviations become positive, and they no longer add up to 0. So over here, you're at a dead end, because they add up to 0. They'll always add up to 0. So the reason why we're finding the absolute values is to make all of the deviations positive, so that they don't add up to 0. Another way to make all of the deviations positive is to square each deviation. What I mean by squaring is multiplying each deviation by itself. If we multiplied -3 by -3, we would get 9. If we multiplied -2 by -2, we would get 4. And if we squared each deviation by multiplying each deviation by itself, we would also get a list of all positive numbers, because squared numbers are always positive. And that would also take care of this problem, because once again, the numbers wouldn't add up to 0. They would all be positive. Let's look at an example of that. If we square each deviation over here, we get all positive numbers, and that also makes it so the column won't add up to 0. Because when you multiply a negative number by itself, you get a positive number. -2 times -2 is 4. -1 times -1 is 1. 1 times 1 is 1. And 2 times 2 is 4. So squaring the deviations is another way of avoiding the problem of the deviations adding up to 0. And if you calculate these squared deviations, and you get this other column here, you can actually use this column to calculate two other values called the variance and standard deviation. And those are the last two measures of dispersion that we'll talk about.
Let's now go over the steps to calculating the variance.
You calculate the mean of the data. You subtract each data value by the mean to get the deviations. You square each of the deviations, so you multiply each deviation by itself. So the first two steps are the same steps these two steps are the same steps that you would follow for the MAD, but step 3 is where it changes, because instead of finding the absolute value of each deviation, we're squaring each deviation. Then you add the squared deviations, and then you divide the total by the number of squared deviations. So basically, the variance is just the mean of the squared deviation column. You're just averaging the squared deviations. But this step right here, where you divide by the number of squared deviations to get the variance, this step is actually adjusted if the data comes from a sample instead of from an entire population. And we'll talk about that adjustment a little bit later. So basically, the variance is just the mean of the squared deviations, and it's adjusted slightly if the data is from a sample. I'll also talk about why you have to use that adjustment later on. So at step 5, we get our variance. And then if you go one step further, and you take the square root of the variance, you get a value called the standard deviation.
We'll go through some step-by-step examples of calculating the variance and standard deviation, just like we did with the MAD. But before we do that, I wanted to show you a quick demonstration of how the MAD, variance, and standard deviation are all able to show the amount of dispersion in the data. This demonstration will show you that the MAD, variance, and standard deviation all increase when the data has more dispersion or more spread. So here's the demonstration. Here's a made-up data set with 4 data values. The 4 data values are 3, 4, 6, and 7. The mean of these 4 data values is 5. If you added these 4 data values and divided the total by 4, the answer would come out to 5. So the mean of this data set is 5. If we subtract each data value by the mean of 5, we get the deviation of each data value. So 3 minus 5 is negative 2, so 3 has a deviation of negative 2. 4 minus 5 is negative 1, so 4 has a deviation of negative 1. 6 minus 5 is 1, so 6 has a deviation of 1, and 7 minus 5 is 2, so 7 has a deviation of 2. If we take this column of deviations and we just leave off the negative signs, we get a column of absolute deviations. And if we calculate the mean of the absolute deviation column, we get the MAD, or the mean absolute deviation. So if we add these 4 absolute deviations and divide the total by 4, because there's 4 of them, we get the MAD, which is 1.5. So this MAD of 1.5 is just the mean of the absolute deviation column. It's the mean of the 4 absolute deviations. If we multiply each deviation by itself, then we get a column of squared deviations. So negative 2 times negative 2 is 4. Negative 1 times negative 1 is 1. 1 times 1 is 1. And 2 times 2 is 4. So we've just squared each deviation. In other words, we've multiplied each deviation by itself, and we've calculated this new column of squared deviations. If we calculate the mean of the squared deviation column, the answer will be called the variance. The variance is just the mean of the squared deviations. So just like how the MAD is the mean of the absolute deviations, the variance is the mean of the squared deviations. They're just the means of 2 different columns. So if we add these 4 squared deviations, the total is 10. And then 10 divided by 4 is 2.5. So the variance, or the mean of the squared deviations, is 2.5. If we put the variance of 2.5 under a square root sign, and we get the square root of the variance, then the answer is called the standard deviation. The standard deviation is just the square root of whatever the variance equals. So the square root of 2.5 is 1.6, so the standard deviation of this data set is 1.6. So we've just found out that this data set right here has a MAD of 1.5, a variance of 2.5, and a standard deviation of 1.6. Now what I'm going to do is I'm going to increase the amount of dispersion in this data set to show you that the MAD, variance, and standard deviation will all increase. What I'm going to do is I'm going to drop this 3 down to 2, and I'm going to raise the 7 up to 8. By dropping the lowest value by 1 and raising the highest value by 1, I'll increase the amount of dispersion in the data, and then that'll cause all 3 of these values to go up. So I just increased the amount of dispersion in the data because, like I said, the 3 went down to 2, and the 7 went up to 8. Now our MAD, variance, and standard deviation have all gone up because, remember, before the MAD was 1.5, and now the MAD is 2. The variance was 2.5, and now the variance is 5. And the standard deviation was 1.6, and now it's 2.2. So all three values have increased because of the fact that the data now has more dispersion. Now let's think about why. Let's think about why the higher dispersion in the data caused these three values to increase. Well, two of our data values are further away from the mean than they used to be, so two of our absolute deviations have increased. This first data value is now 3 away from the mean of 5, so it has an absolute deviation of 3. This last value is also now 3 away from the mean of 5, so it has an absolute deviation of 3. However, this first value used to be 3, which is only 2 away from the mean of 5, so this absolute deviation right here used to be 2. Also, this last value used to be 7, which is only 2 away from the mean of 5. So this last absolute deviation also used to be 2. Basically, two of our values have moved further away from the mean, so two of our absolute deviations have increased. When these two absolute deviations went from 2 and 2 to 3 and 3, it caused the MAD to increase because the MAD is just the mean, or the average, of the absolute deviations. Back when the absolute deviations were 2, 1, 1, 2, the absolute deviations added up to 6, and 6 divided by 4 was 1.5. Now that the absolute deviations are 3, 1, 1, 3, the absolute deviations add up to 8, and 8 divided by 4 is 2. So that's why the MAD went up from 1.5 to 2. So basically, these first and last absolute deviations are responsible for the fact that the MAD increased. When these first and last absolute deviations went up, the MAD went up as well. Now that we understand why the MAD increased, let's think about why the variance increased. When these two absolute deviations went up from 2 and 2 to 3 and 3, it caused these two squared deviations to go up from 4 and 4 to 9 and 9. That's because 2 times 2 is 4, and 3 times 3 is 9. When these two squared deviations went up from 4 and 4 to 9 and 9, it caused the variance to increase because the variance is just the mean, or the average, of the squared deviations. When the squared deviations were 4, 1, 1, 4, the squared deviations added up to 10, and 10 divided by 4 was 2.5. Now that the squared deviations are 9, 1, 1, 9, the squared deviations add up to 20, and 20 divided by 4 is 5. That's why the variance went up from 2.5 to 5. So basically, when these two absolute deviations went up, the MAD went up, and when these two squared deviations went up, the variance went up. Now that we understand why the MAD increased and why the variance increased, let's think about why the standard deviation increased. The reason why the standard deviation increased is basically just because the variance increased. When the variance increases, the standard deviation has to increase along with it. That's because the standard deviation is just the square root of the variance. The standard deviation comes straight from the variance, so when the variance goes up, the standard deviation has to go up along with it. So I hope this demonstration made it clear that the MAD, variance, and standard deviation all increase when the data has more dispersion, and that's why the MAD, variance, and standard deviation are considered measures of dispersion. I also hope that this demonstration made it clear why the MAD, variance, and standard deviation all go up when the data has more dispersion.
Now you might be wondering why the variance and standard deviation are even needed when you could just use the MAD to measure the amount of dispersion in a data set. Well, each of these three measures of dispersion is just a different approach to measuring the amount of dispersion in a data set. Even though they all come out to different numbers, they're all measuring the same idea, which is dispersion. It's like how there's different ways of measuring temperature. On a certain day, I could measure the temperature outside in 3 different ways. I could measure it in Fahrenheit, Celsius, and Kelvin, and I would get 3 different numbers. but those three numbers would all be measurements of the same thing, which is temperature. In the same way, these three values are all measurements of the same idea, which is dispersion. Also, each of these three measures of dispersion has its own advantages and disadvantages. For example, the MAD has the advantage of being easy to interpret. The MAD is just the average distance from each data value to the mean, so the MAD is pretty straightforward. The standard deviation is also easy to interpret because it comes out to a number close to the MAD, so the standard deviation is pretty much the same thing as the MAD. The variance has the disadvantage of being more difficult to interpret. When you see a variance, it's not really clear what it's telling you about the data. Also, even though the MAD and standard deviation are both easy to interpret, the standard deviation has certain advantages over the MAD. For example, later on in this class, we'll talk about how if a population follows a bell-shaped curve, which is called a normal distribution in statistics, it's possible to calculate how many people fall within one standard deviation of the mean, or within two standard deviations of the mean. But that's not possible with a MAD. It's not possible to calculate how many people fall within one MAD of the mean, or within two MADs of the mean. So, since the standard deviation has certain advantages over the MAD, the standard deviation is more commonly used than the MAD is. If you look at an article that reports statistics, you'll almost always see the standard deviation reported, rather than these other two measures of dispersion.
Now that we understand why the MAD, variance, and standard deviation go up when the data has more dispersion, let's go through some step-by-step examples of calculating the variance and standard deviation.
A company has 3 workers, and the 3 workers are 20 years old, 22, and 24 years old. And we want to find the variance at the ages of the 3 people in the population. We have to realize that this is an entire population because the entire company has only 3 workers. So step 1 is finding the mean of the data of the 3 ages. The mean comes out to 22. Subtract each data value by the mean to get our deviations. We're subtracting each value by our mean of 22, which we found in step 1. We square each deviation by multiplying each deviation by itself. -2 times -2 is 4 because the negatives cancel out. 0 times 0 is always 0, and 2 times 2 is 4. These are our squared deviations in this column. Step 4, we add the squared deviations. They add up to 8. And now we need to find the mean of the squared deviations, because the variance is just the mean of the squared deviations. So we divide by the number of squared deviations, which is 3 in this case, 1, 2, 3, and we get our variance of 2.7. And if we want the standard deviation, it's just the square root of the variance. If the variance is 2.7, the standard deviation is 1.6. Now that we've gone through an example of calculating the variance and standard deviation of an entire population, we'll go through an example of calculating the variance and standard deviation of a sample. We'll see that the variance and standard deviation have to be calculated a little bit differently when the data is from a sample. This is an example of calculating the variance and standard deviation with data from a sample. In this example, we've recorded the ages of 3 selected employees from a company that has 1,200 employees. The ages of the 3 selected employees turn out to be 20, 22, and 24. We want to calculate the variance and standard deviation of the heights of the 3 people in the sample. Since these 3
values come from a sample and not from an entire population, we're going to have to adjust the formula a little bit when we calculate the variance and standard deviation.
Step 1 is still the same. The mean is 22. We still subtract each value by the mean to get the deviations. We still square the deviations. And we still add the squared deviations. Step 5, the next step, is the only step that changes when the data is from a sample. Instead of dividing, when it's a sample, instead of dividing by the number of squared deviations, you actually divide by one less than the number of squared deviations. So if there's 3 numbers in this column, we divide by 2. So this is actually called n minus 1. And if we had 5 numbers in this column, we would divide by 4. And if there were 10 numbers in the column, we would divide by 9. We just have to divide by 1 less than the number of squared deviations. Our variance is 4. And just like before, the standard deviation is just the square root of the variance. So if the variance is 4, the square root of 4 is 2, and that's our standard deviation. So the only step that's changed is this dividing step right here. If the data is from a sample, you have to drop it down by 1. And we'll talk about the reason for that adjustment next. So why do you divide by n minus 1? Well, when you calculate the variance and standard deviation of a sample, what you're actually trying to do is you're trying to estimate variance and standard deviation of the entire population. In other words, you're trying to estimate how much spread exists across the entire population that the sample came from.
Whenever a person calculates any value with data from a sample, such as a mean, a percentage, or a standard deviation, the purpose is to estimate what the value would have equaled if it had been calculated with data from the entire population. This is called statistical inference.
And when you calculate the variance and standard deviation of a sample, they actually tend to underestimate what the variance and standard deviation would have equaled if you had used the entire population, if you had collected data from all population members. So the variance and standard deviation of a sample tend to underestimate the variance and standard deviation of the entire population. And that can be a problem because if that's true, then it means that the variance and standard deviation of your sample is giving you misleading information about the entire population. So we have to have a way to deal with this problem. And the way that we deal with that problem is that we use an adjustment to raise the variance and standard deviation of the sample up higher so that they better estimate the variance and standard deviation of all population members.
Basically, when you divide by n minus 1, you're giving a boost to the variance and standard deviation of your sample so that they're less likely to come out too low, so that they're less likely to underestimate the variance and standard deviation of the entire population. Now you might be wondering why dividing by n minus 1 would increase the variance and standard deviation of your sample. The reason why is because when you divide by n minus 1, you're dividing by a smaller number. And when you divide by a smaller number, you get a bigger answer. When you divide by n minus 1, you get a bigger answer that's less likely to underestimate what the value would have equaled if it had been calculated with data from the entire population. Let's now look at a demonstration of how the n minus 1 adjustment helps to prevent the variance and standard deviation of the sample from underestimating the variance and standard deviation of the entire population.
Let's look at this demonstration right here. Here we have a population of 3 people, and now over here I've selected 2 out of the 3, these 2 people, to be a sample of the population. Here I calculated the variance and standard deviation of the entire population. They came out to 2.7 and 1.6. Here I did the same thing with the sample. I got the variance and standard deviation of the sample, but notice how I didn't adjust this number like I should have right here. Since there's 2 numbers in this column, I should have dropped the 2 down to 1. I should have divided by 1 instead of 2. And so basically I didn't use the adjustment that I should have for data from a sample. And what's happening is we can see that the variance of our sample, which came out to 1, underestimated the population variance of 2.7, and the sample standard deviation of 1 underestimated the population standard deviation of 1.6. Both values underestimated the entire population. And if we had used the adjustment, if we had dropped the 2 down to 1 like we should have, what would have happened is the sample values would have come out to bigger numbers, and they wouldn't have underestimated the population by as much. So this adjustment is bringing up these 2 numbers so that they come out closer to what the population values equal, and they estimate them more accurately.
Now you might be wondering why there's a tendency for the variance and standard deviation of a sample to underestimate the variance and standard deviation of the entire population it came from. The reason why is because when you randomly select a sample from a population, there's a tendency for the data in the sample to have less dispersion than the data in the entire population. After all, the population includes everyone, all the way from the lowest person up to the highest person. So the entire population might have quite a bit of dispersion to it, because the population includes everyone, even the extreme people. When you randomly select a sample from a population, the data in your sample usually doesn't reflect the true amount of spread that exists across the entire population. That's why the variance and standard deviation that you calculate with the data from your sample tend to come out lower than the variance and standard deviation of the entire population, unless you adjust the variance and standard deviation of your sample to make them come out to higher numbers. Now you might be feeling a little bit confused because when we talked about other types of statistical inference, such as using a sample mean to estimate a population mean, we said that if the sample is random, the sample value tends to be a good estimate of the population value. And we didn't talk about any type of adjustment being needed. But it turns out that if you want to do a statistical inference in which you use a sample variance to estimate a population variance, or a sample standard deviation to estimate a population standard deviation, you have to do an adjustment to the sample value if you want it to be a good estimate of the population value. And that's true even if your sample was random. We're almost at the end of the video now. I just wanted to make one more point about the MAD, variance, and standard deviation. And then at the end of the video, we'll cover the difference between a sample statistic and a population parameter, which is just a little bit more vocabulary. The last point I wanted to make about the MAD, variance, and standard deviation is that when those 3 values are calculated with the same data set, the MAD and the standard deviation come out to about the same number, and the variance comes out to a number that's quite a bit bigger than both the MAD and the standard deviation. In this example right here, we have data from a population of 5 people, and we've calculated the MAD, the variance, and the standard deviation of the 5 values. We can see that the MAD and the standard deviation came out to about the same number. and the variance, which is in the blue box, came out to a number quite a bit bigger than both the MAD and the standard deviation. We know that the MAD literally is the average distance to the mean, because each absolute deviation is just the distance from that data value to the mean, and the MAD is just the mean of all of those distances. Since the standard deviation comes out to a number that's close to the MAD, you could say that the standard deviation is roughly the average distance to the mean. So the MAD literally is the average distance to the mean, and the standard deviation is a number that's roughly the average distance to the mean. That's why people usually say that the MAD and the standard deviation are conceptually the same thing. They're pretty much interchangeable. So now that I've made this last point about the MAD, variance, and standard deviation, we'll talk about the difference between a sample statistic and a population parameter. Any value that's calculated with data from an entire population is a population parameter, and any value that's calculated with data from a sample is a sample statistic. At this point, you might be wondering why they don't just call them sample statistics and population statistics. Why do they have to use the word parameter? Well, it's really just statistical jargon. In statistics, they decided that they wanted to have one word for a value calculated from a sample and another word for a value calculated with data from an entire population. So don't worry about why this one is called a statistic and why this one is called a parameter, because they are pretty much just sample statistics and population statistics. So let's look at some examples. Let's start by looking at some examples of population parameters. The mean of a population is a population parameter, so the mean age of all college students in the US would be a population parameter. The median of a population is also a population parameter, so if you found the median age of all college students in the US, that number would be a population parameter. The standard deviation of a population would also be a population parameter. So if you were somehow able to calculate the standard deviation of the ages of all people in the US, that number that you calculated would be a population parameter. I said that any value calculated with data from a sample is a sample statistic. So let's look at some examples of sample statistics. The mean of a sample would be a sample statistic. So if I randomly selected 250 college students who live in the US and calculated the mean age of those 250 people, the value that I calculated would be a sample statistic. The median of a sample is also a sample statistic. So if I selected 250 college students who live in the US, recorded their ages, and I found the median of those 250 people, that median would be a sample statistic. A standard deviation that's calculated with data from a sample is a sample statistic. If I selected 250 college students who live in the US, recorded their ages, and then I calculated the standard deviation of those 250 ages, the value that I've calculated would be a sample statistic, because it was calculated with data from a sample. So I said that any value calculated with data from an entire population is a population parameter, and any value calculated with data from a sample is a sample statistic. Usually, population parameters can't be calculated because a population parameter can only be calculated after data has been recorded from all members of the population. And we know that it's usually not possible or practical to collect data from all members of a population. So, since researchers usually can't calculate population parameters, what they do is they collect data from samples, preferably random samples, and then they calculate sample statistics to estimate the population parameters that they're interested in. And we said that the process of calculating a sample statistic to estimate a population parameter is called statistical inference. So using a sample mean to estimate a population mean is statistical inference. Using a sample standard deviation to estimate a population standard deviation would also be statistical inference. Now let's end the video by looking at some of the symbols that are used for common population parameters and for some common sample statistics. The symbol for population mean is the Greek letter mu, which looks like the letter U. The symbol for a population variance is the Greek letter sigma, which looks like an O, with this exponent at the end, and it's called sigma squared. And the population standard deviation symbol is just sigma. The reason why the population variance is sigma squared and the population standard deviation is sigma is because the standard deviation is just the square root of the variance. The symbol for a sample mean is x bar. It's called x bar, but it's just an x with a bar above it. The symbol for a sample variance is s squared, and the symbol for a sample standard deviation is just the letter s. So all of the symbols for population parameters are actually Greek letters, and all of the symbols for sample statistics are just regular letters, just common letters. So if you're reading an article and someone is reporting a sample mean, a person might just say x bar equals this number. Instead of saying the sample mean is this number, they might just say x bar equals this number. Or if they're reporting a sample standard deviation, the article might just say s equals this number. So this is the last point that I wanted to make in this video. So thank you for watching.